in the last lecture we derived the magnetic vector potential for the Hertz dipole. We saw Hertz dipole is the basic unit on which we can develop and we can find out the fields for more complex current distributions. So, the analysis of Hertz dipole is very important, because once we understand the fields developed by the Hertz dipole, we can always find the electric and magnetic fields generated by any other current distribution. So, we had got this Hertz dipole, which is nothing but a small current element, and from there we got the magnetic vector potential. We considered a coordinate system and the Hertz dipole is oriented in the z direction, and from there we found that the magnetic vector potential at any point in the space will be oriented in the same direction as the current element. That will be everywhere in the space we will have the magnetic vector potential which will be oriented in z direction. So, the magnetic vector potential at a distance r from the origin essentially is given by this, which we wrote explicitly as the z component, which was essentially given by that. Now, since we are talking about the spherical coordinate system and we are going to investigate now the fields in the spherical coordinate system, essentially we have to convert this a z component in the appropriate spherical components, that is the r component and the theta component. So, note here, if this is a radius vector, this is the direction which is theta direction. The radially outward direction, this direction is the r direction, and phi direction is perpendicular to the plane of the paper, which is going this way. So, this vector potential does not have any component in this direction perpendicular to the plane of the paper, that is 90 degrees with respect to this. So, the vector potential in the spherical coordinate system would have two components, the r component and the theta component. So, since this angle is theta, this angle is also theta. So, this component will be a z cos of theta. This component will be negative of a z sin of theta. So, you will have theta component which is minus a z sin theta and r component which is a z cos theta. So, from here we get now the component for the spherical coordinate system. So, I have from here a r is equal to a z cos of theta, a theta which will be minus a z sin of theta, and a phi in this case is equal to 0, where a z is essentially this quantity. So, if you put the whole thing together, that is this quantity a z. Now, once we have the knowledge of the vector potential, then we can go now to the definition of the vector potential, and from there we can find out the magnetic field. We can use mu times H, which is B, is equal to del cross of A, or the magnetic field H is 1 upon mu del cross A. So, once I know these components of the vector potential a r, a theta, a phi, then I can substitute into this and I can get the magnetic fields. Write in this curl explicitly this is equal to 1 upon mu, and I can write the curl in the spherical coordinate system, which is 1 upon r square sin theta, determinant r theta, r sin theta, unit vector phi, d by dr, d by d theta, d by d phi AR R A theta R sin theta A phi. Now, since the current element which we have got here is symmetric in the phi direction, because it will appear same no matter from which direction we see, only when we see in different direction in theta the element will appear differently. So, if I see from this direction in theta, it will look like a line, when I see from the top it will look like a point, and so on. So, we have a theta dependence for this current, but there is no phi dependence because it appears symmetric from all directions. As a result, this quantity d by d phi is identically equal to 0 in this case, and we also have seen that the phi component of the magnetic vector potential is also 0. So, substituting now into this, we get the magnetic field H, that is equal to 1 upon mu r square sin theta determinant r theta r sin theta phi d by dr d by d theta d by d phi is 0. Then the r component AR, which is AZ cos theta. So, this is AZ cos theta. The theta component is minus AZ sin theta. So, this is minus AZ sin theta, and the phi component is 0. So, you get this is 0. So, the vector magnetic field essentially is given by the determinant, which is this. Now, it is immediately clear that since these two elements are 0 here, the r component and the theta component are identically 0. So, only component which we will get will be corresponding to the phi component, which will be d by dr of this quantity minus d by d theta of this quantity. So, essentially what we get from here, we get H r is equal to 0, H theta is also equal to 0, and H phi equal to 1 upon mu r d by dr of minus AZ sin theta minus d by d theta of AZ cos theta. From here, d by dr of minus AZ sin theta minus d by d theta of AZ cos theta. So, this is the phi component of the magnetic field. Substituting now for AZ from here, that AZ is this quantity, and taking derivatives with respect to r and theta, we can get the magnetic field phi component, which is equal to I0 dl e to the power j omega t minus j beta r sin theta upon 4 pi r, or I can take r inside the bracket. This will become j beta upon r plus 1 upon r square. So, the Hertz dipole essentially generates the magnetic field which are phi oriented. That means, the magnetic field essentially are going round this current element. So, no matter where you go in the space, essentially they will be essentially spiraling around this z axis, because that everywhere they are going to have the phi component. So, magnetic fields, as we would have got, suppose this current element was of infinite length, we would get the magnetic field from the Ampere's law, which will be like the loop around this. The same kind of magnetic field is generated by this current element also. Once we get the magnetic field, then we can go to the Maxwell's equation, and now we want to find out the electric field not at a location of the source, but somewhere in the space where there are no charges or no sources. So, essentially we can substitute the magnetic field in the source free Maxwell's equation and then find out what is the electric field. So, we can take this magnetic field now and substitute into the source free Maxwell's equation, which is del cross H, that is equal to j omega epsilon times E. And since I know H, I can find out E. So, the electric field now at the observation point, that will be equal to 1 upon j omega epsilon del cross H. Again I can use the determinant in spherical coordinates. So, this quantity will be 1 upon j omega epsilon 1 upon r square sin theta r theta r sin theta phi d by dr d by d theta d by d phi which is 0, because we have seen earlier that there is a symmetry in phi. So, this quantity will be 0, and now we do not have a component which is HR component for the magnetic field. There is no theta component for the magnetic field. The component which we have is only phi. So, HR is 0, S theta is 0. So, I can substitute this quantity is 0 first, this is 0, this is 0, and this is phi. Now, again simplifying and taking out the components. So, the r component essentially will be d by d theta of h phi, and this quantity theta component will correspond to the derivative of this quantity d by dr of h phi. So, now just taking this derivative and separate out, you get the component E r that will be equal to I 0 d L cos of theta e to the power j omega t minus j beta r upon 4 pi omega epsilon beta upon r square minus j upon r cube, and theta component E theta will be equal to I 0 d L sin theta e to the power j omega t minus j beta r upon 4 pi epsilon j beta square upon omega r plus beta upon omega r square minus j upon omega r cube, and the phi component of the electric field is identically 0 in this case. So, now note here the magnetic field for the Hertz dipole will be going around the z axis, which is like that. But for the electric field we have two components, one is the r component which is like that, and other one the component which is in theta direction, which is like this. So, depending upon the location, this electric field direction will be changing. The magnetic field direction will change only in this plane, which is parallel to the x y plane, because it has only the phi component. Now, up till now the derivation is very straightforward. Essentially what we did, we took the magnetic vector potential, substituted into the Maxwell's equation, found the magnetic field. Once we have the knowledge of magnetic field, we again substituted into Maxwell's equation and we got the electric field. Now, we try to look at these terms which we have got, various terms, into the electric and magnetic fields. So, if I look in general the field expression, the H phi and these two components ER and E theta, I notice there are three types of field which are generated by the Hertz dipole, depending upon the variation of the field as a function of distance. One variation is 1 over r, other variation is 1 over r square, and the third variation is 1 over r cube. Same is for magnetic field. We do not have 1 over r cube term, but I have 1 over r square and I have a term which is 1 over r. We know that from the Ampere's law that if I have a current, then it produces the magnetic field, and the magnetic field has a variation from a current that varies as 1 over r square. So, I know this term which is varying as 1 over r square is same as what we used to get from the simple Ampere's law. This phenomena was the induction phenomena. So, if you had a current, it would produce the magnetic fields around it, and that magnetic field had a variation which was 1 over r square. So, this term which varies as 1 over r square we call as the induction term. So, we have these fields, we denote them induction term because it was the magnetic induction I had when the current was flowing in the wire. However, if I look at the electric field here, I have a term which varies as 1 over r, and I also find a term which is 1 over r cube. Now, this term which is 1 over r is a term which we have not seen before. This is a term which is the new term, this term beta upon r, or same term here which is varying as 1 over r. And that is the term essentially we will try to interpret in detail, because that is the one which is contributing to the radiation. So, firstly we have three types of fields. One over r variation, 1 over r square variation, and 1 over r cube variation. This term, as we already saw, we call as the induction term or induction fields. The 1 over r term, which is a new term, that is the term which we call as the radiation field. And the third term, which varies as 1 over r cube, we call as the electrostatic field. And we will try to understand why the terms are called that way. The induction term is very clear because that is the way the magnetic induction was due to a current. So, 1 over r square field is a very familiar field, we have seen it earlier, and using the same understanding we call that field as the induction field. If I look at this field which is varying as 1 over r, if I look at the expression here, this is the quantity which is beta square upon omega, and as we know beta square is nothing but omega square mu epsilon, that is what we have seen earlier. So, this quantity whatever we have, that varies as omega square mu epsilon upon omega r. So, this field 1 over r, that varies as omega mu epsilon upon r. That means, this term which is varying as 1 over r, it is proportional to frequency. So, this quantity 1 over r term, this is proportional to omega. If I look at this term here which is beta upon omega r square, since beta is proportional to omega, this term is independent of omega, and this term is inversely proportional to omega. So, this field induction field is independent of omega, and this field electrostatic field whatever we are calling, which is varying as 1 over r cube, this is inversely proportional to omega. So, 1 upon omega. So, as we go to the lower frequencies, this is the term which is going to dominate. This term is independent of frequency, so it is always present, and this phenomena is essentially high frequency phenomena. So, what that means is that this field whatever is the radiation field is a high frequency phenomena essentially, and that is what is the radiation, that when we go to the extremely low frequencies there is no radiation. As I go to higher and higher frequency, for the same current I0 into dl, we will have now this term dominating more and more as the frequency increases. That means, for the same current amplitude, if the frequency is increased, the dominance of this field increases. So, radiation becomes stronger and stronger for the same current as the frequency increases, and that we understand from our basic argument which we have put for the radiation, that as the frequency increases the rate of change of current increases, that means the charges get accelerated, decelerated in a more way, and because of that we have more radiation field. So, this relation that the radiation field is proportional to omega agrees with what basic understanding we had put forward for getting a radiation from the current. This variation also is okay because this is the field which is even generated by the DC current. So, its independency for omega is also understandable. What is the origin of this field which is varying as 1 upon omega? That means, this field is going to be more dominant as we go to lower and lower frequency. As with term we calling it here electrostatic field, that means this must be related to some kind of charges which are there, but we have not put any charges anywhere in our analysis. We simply assume there is a current I which is flowing into this current element, and then we investigated the fields which are induced because of this small current element. However, if you look at very carefully, now one can ask a question. This is my current element, let me enlarge it a little bit. Current is flowing into this current element. Where does the current go? The current flows into this. So, one half cycle the current will be flowing upwards, in the other half cycle the current will be flowing downwards, and there is no closed path now for this because these things are closed by the fields. So, essentially when the current is flowing in this direction, the electrons are moving downwards positive charges effectively are going upwards. So, when the current goes upwards, there is accumulation of charge on these 2 points, on the 2 ends of the current element. So, when the current flows this way, the positive charges are moving here and the negative charges will be moving in this direction. So, in one half cycle, the positive charges will get accumulated at this end and the negative charges will get accumulated in this end. In the next half cycle, when the current reverses direction, the negative charges will get accumulated here and the positive charge will get accumulated here. So, essentially this current flow which we are talking about, which is time varying, is equivalent to having a time varying charges which are accumulated at the 2 ends of this current element, which is saying that I am having a electric dipole whose charges are changing as a function of time and they essentially give you this current in this element. So, essentially you are having a dumbbell of charges, equal and opposite charges, which are located at the 2 ends of this current dipole. So, as the current is oscillating positive and negative, this dumbbell essentially is oscillating. So, it is positive, next half cycle will be negative and so on. So, essentially we are having a oscillating dumbbell which is equivalent to the current flow which we are here. So, though we did not say explicitly when we started with this current in this small current element that there are charges in this system, we simply started with a current flow in this small current element. These charges will get accumulated at the ends of the Hertz dipole and then they will produce their field which will be electrostatic fields. So, if I consider this electric dumbbell and now find out what is the field produced because of these charges, I can find out some observation point which is very close. So, let us say I take some point here, some point here, I put some test positive charge, so I will get the field which is like this, the field will be like this. So, resultant field will be always the vector sum of these 2 fields which is produced because of these 2 charges. One can show that this field now varies as 1 over r cube, where r is the distance from the center of this dipole. So, this term which we are getting here 1 over r cube term is essentially electrostatic because this field is produced by the dumbbell of these electric charges which are separated by a distance dl. So, if I just without getting into the time varying thing, if I consider 2 equal and opposite charges separated by a distance dl and find the field produced by these charges, then I will get the resultant field which will vary as 1 over r cube, and that is what is the field which we have got here. Why this field then varies as 1 over frequency? Because if the frequency becomes smaller and smaller, for the same current more and more charges get accumulated here, because the charge essentially is integral of the current over time. So, if I have a time period which is very large, for the same current amplitude I will be accumulating charges over the time period, and as the time period increases I will get more accumulation of the charge. So, as the frequency becomes smaller and smaller, the amplitude or the amount of charge which will get accumulated on the ends of the Hertz dipole will go on increasing, and one can see that when you go to frequency which is DC, the current will always flowing upwards, and then if I take as a steady state in finite time, these charges will go to infinity. So, as the frequency goes to 0, this field essentially blow to infinity, because in steady state there will be infinite charges which will be resting on the 2 ends of this dipole. So, this nature that the field which we have got here is because of the charge, which is now the collection of the charges which are due to the current should vary inversely as a function of frequency, because lower the frequency, that means more accumulation of the charges, and higher will be the field because of this electrostatic charges. So, this field therefore then we call electrostatic field, with this field we call induction field. And why there is no 1 over r cube variation for the induction field? Because there is no magnetic charge accumulation. So, we get a variation which is 1 over r square, which is same as the induction field, and we get a field which is 1 over r, which is the one which is radiation, which should contribute to the power flow, as we will see little later. So, this field is the new field which the magnetic field has. There is no equivalent of 1 over r cube term here, because there is no accumulation of the magnetic charges. For the electric field, we have accumulation of electric charges, and because of that we get a field which will be electrostatic field, and that will vary as 1 over omega. So, these three fields now, the radiation field, the induction field and the electrostatic field, will be generated by the simple dipole, Hertz dipole. Our interest however is only in this field, because we are investigating now only the radiation fields. So, we will try to only take that component of the field which will be varying as a function of omega. So, what we conclude from this analysis is that you take any time varying current, the time varying current is going to generate three types of fields. One which will vary as 1 over r, and this field will be linearly proportional to the frequency. The other field which will be varying as 1 over r square, and this field is independent of frequency. And third one is the electrostatic field, which will vary as 1 over r cube, and this field will vary as inversely proportional to the frequency. Interestingly, one can see from the expression for these fields that all these three terms become equal. So, I can take the magnitude of this term and make it equal to this. For the same distance, even this term will become equal to this. So, if I take a distance from the current element where these terms will become equal, so I get a distance beta square upon omega r equal to beta upon omega r square. One beta will cancel, omega will cancel, r will cancel. So, from here I get r is equal to 1 upon beta, which is nothing but 1 upon 2 pi upon lambda. So, this is lambda upon 2 pi. Taking approximately pi 3.14, so this is taking approximately this quantity as 6, we say that approximately at r equal to lambda by 6, these three terms will become equal in magnitude wise. So, we have, if I go from the Hertz dipole at distance lambda by 6 approximately, then the radiation field, the induction field and the electrostatic field would be equal. And as I go less than lambda by 6, this term will increase, this will increase further, and as I go beyond lambda by 6, this term would have died down rapidly. Only term which will survive will be this term. So, if I plot this now as a function of distance, the different fields, so this is E magnitude, I am plotting as a function of distance. I will have three types of fields. One is the electrostatic field, which will be like this. Other will be the induction field, which will be like that, and third will be the radiation field, which will be like this. And this is the point which is lambda by 6 approximately, or lambda by 2 pi to be precise, where these three fields are going to be equal. So, this is 1 over r, this is 1 over r square, and this is 1 over r cube. As we see, as we go to lower and lower frequency, this is the term which will dominate. So, if I go very close to the Hertz dipole, essentially the influence will be only the electrostatic field. If I somewhere in between, then I will get the induction field, and if I go very far away from the dipole, very far away means much larger compared to lambda by 6, then practically the radiation fields will be present in the medium. So, now this distance lambda by 6 is now the reference point, and on the basis of this distance with respect to this, I can now divide the field into two categories. So, if I go to a zone which is very short compared to lambda by 6, I call those fields as the near fields, and those fields will be essentially dominated by the induction and the electrostatic fields. Whereas, if I go to a distance which is much larger compared to lambda by 6, then the field which will be dominated will be only radiation field, and I call that field as the far field. So, now depending upon the distance, I now classify the fields. So, we say near field, this for r much less than lambda by 6, and then we have fields which are called the far fields, which will correspond to r much greater than lambda by 6. Ideally, if you want only 1 over r term, which is the radiation field, then we should go to a distance almost tending to infinity, where 1 over r square and 1 over r cube field would have died down to a substantially low value, and I will get a field which is only 1 over r, which is the radiation field. So, basically we see now something interesting, and that is, if I go now very close to the Hertz dipole, we have a term which is 1 over r square and 1 over r cube. So, I will have a component which is this component E theta. I will have a component which is E r, because it has term r square, 1 over r square and 1 over r cube. The magnetic field will have a term which is 1 over r square. But if I go to the zone which is far field zone, where r is much greater than lambda by 6, then these fields are negligibly small. So, I will get only radiation field. There is no radiation field component corresponding to ER. So, this will be negligibly small. So, this will be taken as 0, and we will have a theta component which will be given by that. So, what we see in near field, we will have a component ER, E theta and H phi, all three components will be present. Whereas, when I go for the far field, the ER component is negligibly small, and we will have only two components, which is E theta and H phi. Since we are interested here only in the radiation field, we can take appropriately only those terms which are having 1 over r variation. So, I can take this quantity is 0 now. So, this is the term which gives me radiation field. So, I can write down only for far field, that is what our interest is. We get the component E theta, which is j I 0 dl beta square sin theta e to the power j omega t minus j beta r upon 4 pi omega epsilon r, and we get h phi that will be equal to j I 0 dl sin theta beta e to the power j omega t minus j beta r upon 4 pi r. So, for the far field we have only these two components. Again, few things can be noted here. Firstly, both the fields have a variation as a function of angle theta as sin theta. That means the fields are 0 at theta equal to 0 and fields are maximum at theta equal to 90 degrees. So, that means both the fields are maximum in this direction when theta equal to 90 degrees, and along the length of this Hertz dipole, that means along the axis of the dipole, these two fields are identically 0. One observation. That means the fields are not uniformly created in the space, they have a directional dependence. You have a maximum field when we go perpendicular to the Hertz dipole, and along the Hertz dipole the fields, these far fields, are identically 0. Second thing what we note from here is, if I take a ratio of these two quantities, or before that, the electric and magnetic fields have this term j with respect to this current I 0 e to the power j omega t. That means the field which are now generated, what we call as the far field or radiation field, they are 90 degrees out of phase with respect to the current. And what is the reason for that? The reason is simple, that right from beginning we said the radiation is a phenomena which is related to the rate of change of current. So, if you are having a time varying current which is e to the power j omega t, the rate of change of current will be equivalent to multiplying the quantity by j omega. So, you have the fields which are 90 degree out of phase with respect to the current. So, this j which you get here in this field essentially supports our basic argument which we had for the radiation, that if we accelerate the charges, that means if you have a rate of change of current, we will get the radiation fields. That is what we see from here. The third thing which we note from here is, if I take a ratio of this quantity E theta and H phi, this quantity will cancel, I 0 dl will cancel, sin theta will cancel, r will cancel, 4 pi will cancel. But what we will get? We will get beta square here, and here we will get beta. So, the ratio of these two quantities, if I take E theta and H phi, that will be equal to beta upon omega epsilon. And I know this beta is nothing but omega square root mu epsilon divided by omega epsilon. So, this is equal to square root of mu upon epsilon, which is nothing but the intrinsic impedance of the medium eta. So, note what we have got here, the wave which we have got now, or the field which we have got, this represents a spherical wave. That means the wave is travelling in the r direction. That is what we, right from the beginning we got from the solution. We got a component E theta for the electric field and component H phi for the magnetic field, which is perpendicular to the plane of the paper. And ratio of the electric and magnetic field is equal to the intrinsic impedance of the medium. That means these fields are having exactly identical properties as we used to have for uniform plane waves, that the electric field, the magnetic field and the direction of the wave propagation are perpendicular to each other. That is what we have here. The wave propagates in r direction, the field is in theta direction, electric field, and the magnetic field is in phi direction. So, these three are perpendicular to each other, and the ratio of the electric and magnetic field is equal to the intrinsic impedance of the medium. So, this wave is spherical wave and it has a transverse nature, that the electric and magnetic field both are transverse to the direction of the wave propagation. So, we have got here what is called a transverse spherical electromagnetic wave, and it has properties, all properties of transverse electromagnetic wave, like the ratio of the electric and magnetic field should be decided by the medium properties, which is the intrinsic impedance of the medium, and electric field, the magnetic field, and the direction of the wave propagation should be perpendicular to each other. So, though the wave which is created by this is spherical, every point in space, if you go around this Hertz dipole, you will see a transverse electromagnetic wave. Though the direction of the transverse electromagnetic wave will be varying at different points in space, but at any location, if you ask what is the nature of the electromagnetic wave, it is a transverse electromagnetic wave. So, essentially, if I take the observation point, draw a sphere passing through that point, the radially outwards direction gives me the direction of the wave propagation, and the tangents which are drawn to the surface at that location perpendicular to each other, they give you direction of the electric and the magnetic fields. We can also see some interesting things from here, and that is the electric and the transverse nature of the electromagnetic wave is there at every point in space, and its direction will be changing when we go to different locations. But at a given point, how the electric field is varying as a function of time. So, let us consider this point here. The electric field is having a theta component, which will be positive or negative. That means at this location, the electric field is always oriented in this direction as a function of time. That means this wave is a linearly polarized wave. The direction of the electric field will change from location to location. Here theta direction is this. If I go to a point here, theta direction will be vertical. If I go here, theta direction will be like that. So, from one location to another location, direction of the electric field will change. But if I ask what is the polarization which is the direction of the electric field at a particular location, that wave is linearly polarized. So, now we have got a very interesting conclusions, and that is, if we consider the small current element, what is called the Hertz dipole, then it generates a variety of fields. It generates induction field, it generates electrostatic field, it generates radiation field. However, if we take only the radiation fields, then these radiation fields satisfy all the properties which the transverse electromagnetic wave has. So, it generates a spherical wave, but the electric and magnetic fields are perpendicular to each other, and they are also perpendicular to the direction of the wave propagation. Also, the ratio of the electric and magnetic field is equal to the intrinsic impedance of the medium. And the polarization which the wave has at any point for the Hertz dipole will be always linear polarization. So, the Hertz dipole essentially generates an electromagnetic wave which is spherical, but is linearly polarized. So, on this concept then we will develop more, and then we will try to investigate more practical antenna systems. We will see how much power is radiated by the current element, and so on and so on.